As a trained meteorologist, I like to say we were one of the first users of supercomputers because there was this great need to understand where the weather was happening over many different locations.
Weather centers, they'll run their models under all sorts of various initial conditions. They perturb them, and they run this thing many times to basically tell you what is the probability of it raining tomorrow or next day and so on and so forth. And these models require big supercomputers.
Summit is our largest supercomputer for science. We've used it for climate change. We're looking at doing simulations of quantum computers. We look at chemistry, quantum materials, large-scale materials. I can go on and on about the numbers of different applications that Summit will do. Algorithms are a process. They're a map that tells you how to get from one place to another. So they give you steps 1, 2, 3, 4, all the way to the end. It's important to understand that these algorithms, they're telling you how to get the answers that you need for a problem. You need a different algorithm depending on the problem you're solving. So if I say to Juan, I need to know the temperature in 30 years and how much it will change, he designs an algorithm that will do several things. It'll tell you actually what the temperature will be with the best certainty we know. It'll get you there faster, so we need the answer quickly. We can't wait 30 years to get the answer from our computer. And then it does it as efficiently as possible on a supercomputer.
These big computers are used to run models, very complicated models. Some folks are actually working on the hardware, the microelectronics, the algorithms that run these models, the numerical analysis that makes these predictions accurate. On the scalability, which deals with the computational complexity of these things. And so it's this interaction that actually allows us to rip through the challenges, both the mathematical and the computational challenges of these problems.
A supercomputer only works because all the processors are working in harmony together over many different processors. The same thing is true with our scientists and all those of us who work here at the lab and our collaborators at academics and industry.
Within the mathematics community, and particularly in SciEm, for example, people like Kate Evans, myself, and others are encouraging this sort of idea of complex systems, as in complicated systems. What happens if you mash up these horrendously difficult problems, like, for example, a socioeconomic model with a climate model? And so not only are you doing things that go across disciplines, but now you have to start thinking differently.
Most computational scientists are a member of a number of societies, both those for the domain and computer science, but SciEm bridges the two. It actually is a great home for computational scientists like climate scientists.
SciEm is one of the premier applied and industrial mathematics societies in the world, and it has created a unique community of mathematicians who are interested in applied problems. Let's encourage very smart people, especially people coming with diverse backgrounds, to say, okay, maybe there are quantitative, precise techniques that we can use to tackle these things. So I'm hoping there is a social and also an intellectual revolution within mathematics or science in general that can handle these very complex problems. And so what I'm hoping is that we develop this capability of taking science, which is very good at compartmentalizing and looking at the thing very specifically, especially mathematics is like that, and somehow say, well, maybe there is a way to do this science in a way that is more comprehensive. And maybe we can be precise as to how all these pieces interact. Now what we do is we engender a group of people who are interested in seeing how precision can be achieved across different disciplines.
SciEm is one of those few interdisciplinary professional scientific societies. They really cover a broad area of not just the science area that you cover, but also it has industry, academics, and national lab members. The science of today is not like the science of the 1700s. You'd have some old lord sitting in the basement of his big castle where he'd uncover some new chemical. Science today is a team sport. It's going to require people with lots of different backgrounds to work together to unlock the secrets. We need atmospheric scientists, ocean scientists, ice scientists, plant scientists. All of those are required to solve those big challenges.
The signature of my career is doing interdisciplinary work and being able to even consider other things that I never would have considered before. We are creating new ways of doing the business of science and engineering.